Hello and welcome to another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler and today we'll be doing Unit 3, Lesson 1 on linear change. Now Unit 3 in our Algebra 2 course is all about linear functions. But before we really launch into linear functions and y equals mx plus b and all of that stuff, I really want to talk about linear change and what it means for a variable or variables to change in a linear fashion compared to one another. So let's jump right into that. All right, linear change. The simplest of all functions are those that are linear. Linear functions arise when the output of the function changes at a constant rate compared to the input of the function. This is known as linear change, and let's take a look at an example of it in exercise number 1. A conveyor belt is dumping sand on a pile such that the height of the pile is increasing at a constant rate of 3 inches per hour. Let h represent the height of the sand pile, and let t represent the time since the conveyor belt started running for the day, where t is measured in hours. Letter A. Represent the rate information given in the problem as an average rate of change. Use proper delta notation. All right, so this is cool, but let's do it together, all right? So remember, the little triangle in our course, what is known as the Greek letter delta, stands for the change in. So what we know right now, and actually let me just use a highlighter really quick to highlight this information, right? What we know right now is that the height is increasing at a constant rate of 3 inches per hour. Very, very important information, all right? So how do we represent that with delta notation? We say that the change in the height divided by the change in time is equal to 3 inches divided by 1 hour. And you could just write it as 3 inches over hour if you want, where the 1 is implied. But it's really nice to kind of think about this. The change in height is 3 inches for every 1 hour that time changes. All right, let's take a look at letter B. How much will the height of the sand pile change every 5 hours? Well, this is super easy, right? We're looking for a change, right? We want delta H, but think about this for a moment. This should make all the sense in the world. Delta H, in this case, will be delta H over delta T times, actually let me use a little dot, times delta T. I mean, think about this, right? Of course, delta H equals delta H over delta T times delta T. The two delta T's would cancel out, and delta H is equal to delta H. The change in H is equal to the change in H. So really, right, the change in H in this case is going to be 3 inches per hour times 5 hours. The hour units cancel, and we get 15 inches. Now, I really want you to understand, that is not what the height is. That is how much the height has changed. Specifically, we can interpret that as the height has increased by 15 inches for every 5 hours of time that pass. And that makes sense, because for every hour that passes, it increases by 3 inches. So let's keep going. Let's take a look at letter C. After 3 hours, the sand pile has a height of 54 inches. What will be its height after a total of 12 hours? All right, now again, right, this is critical. We know that the sand pile is growing at a rate of 3 inches per hour, or its height is growing at a rate of 3 inches per hour. What I'd like you to do is pause the video right now and try to use that information along with that rate information in letter A to figure out what the height of the sand pile will be after 12 hours. I'm going to use a little function notation, a little delta notation right here, right? So I want the height after 12 hours, a little function notation, and that's going to be really the height after 3 hours plus the change in height that occurs from 3 hours to 12 hours, right? Simple as that, right? So the height after 12 hours is going to be the height after 3 hours plus however much the height has changed. Well, let's figure that out. Right now, we know that the change in time between 3 hours and 12 hours will be 12 minus 3, or 9 hours. That means that the change in height, which is 3 inches per hour, times 9 hours will be 27 inches. In other words, from the 3-hour mark to the 12-hour mark, the height of the sand pile has grown by 27 inches, which now allows me to say, right, that the height at 12 inches is going to be the height after 3 hours, which is 54, plus 27, and that is going to end up being a height of 81 inches, right? So the height after 12 hours is the height at 3 hours plus the change in height between those two periods of time. Let's take a look at letter D. What was the height of the sand pile when the conveyor started for the day? Right? We can't assume that it was 0 inches, and in fact, it wasn't. So what I'd like you to do is pause the video now and again, try to use the fact that at 3 hours we know the height of the pile is 54 inches, and we know that it was growing at a rate of 3 inches per hour to figure out what the height of the sand pile was when the conveyor started for the day. Well, remember, we know, let's see, that h of 3 is 54 inches. What we really want is h of 0, right? What was the height of the sand pile at the start of the day? All right, well, here we can say that the change in time between those two is 3 hours, and we can say that the change in height will be 3 inches per hour times 3 hours, and that's 9 inches. Now, that's not the answer to our question, right? That is just how much the sand pile grew between the start of the day and the height that it was at after 3 hours. So now we have to kind of go backwards, right? Let me just extend my page a little bit. And we have to say that the height at 0 is now the height at 3 minus the change in height between the two, not plus because we're going backwards in time. That's going to be 54 inches minus 9 inches, and that means we must have started the day with a height of 45 inches. All right, so we had to kind of go backwards. And if you wanted, you could set it up as h of 3 equals h of 0 plus delta h, which means that h of 0 equals h of 3 minus delta h, which is where we are down here. Okay, linear change. A constant rate at which one variable is changing compared to the other variable, and most often, right, the input variable in these situations in real-world problems happens to be time. And then the rate happens to be something per time, per second, per hour, per minute, per year, per day, etc. Let's keep working with linear change. All right, constant rate of change equals linear. Whenever linear change is occurring, the rate at which the two variables change compared to one another is constant. We can take advantage of this constant rate of change to predict output values. So let's take a look at exercise number 2. The temperature inside a greenhouse is increasing at a constant rate. At 6 o'clock a.m., the temperature of the greenhouse was 64.5 degrees Fahrenheit, and at 11 o'clock a.m., the temperature was 71 degrees Fahrenheit. Letter A, what is the rate of change of the temperature? Use proper units. Great. Well, why don't you go ahead and pause the video now and see if you can figure out what the rate of change is of the temperature in this particular problem. Well, I'm going to use capital F for Fahrenheit as opposed to capital T for temperature, just because I'm going to use lowercase t for time here. So what do I know, right? I want to know what the change in the Fahrenheit temperature is. Wow, red is coming out a lot today, compared to the change in time. All right. I know that I have 71 degrees Fahrenheit minus 64.5 degrees Fahrenheit. Maybe put the little discrete symbol there, divided by 11 minus 6. Okay, that's then going to give me 6.5 degrees Fahrenheit divided by 5 hours. And if I want that as a unit rate, all I have to do is do that division on my calculator or in my head or whatever, And we end up getting 1.3 degrees Fahrenheit per hour. And of course, we can interpret that by saying that the temperature is increasing by 1.3 degrees Fahrenheit for every hour that passes. It's as simple as that. Let's take a look at letter B. Use the rate to determine what the temperature was at 10 o'clock a.m. This is known as interpolation because the prediction is inside of the two known data points. All right, now this is an important idea that comes up in science all the time. When we know sort of two sets of data, right, one at 6 o'clock a.m. and one at 11 o'clock a.m., and we want to make a prediction between those two, it's known as interpolation. It's like inside of the data, right? So we want to do exactly what we did in that previous problem in exercise number 1. We want to try to predict what the temperature is at 11 a.m. So let's do this one together. Now, I could use either my point at 6 a.m. when the temperature was 64.5 degrees Fahrenheit, or I could kind of go backwards and use the one at 11 a.m. when the temperature was 71 degrees Fahrenheit. I think I'm going to go at the 6 a.m. mark. So let's do this one together. All right, so what do I know? And again, what I know is that I've got from t equals 6 o'clock a.m. to t equals 10 o'clock a.m., I know that my change in time is 4 hours. So what I'd like to do is I'd actually like to figure out what my change in temperature is, all right? So the change in F at this point is going to be 1.3 degrees Fahrenheit per hour, right, times that 4 hours. And that's going to give me a change in temperature. I can just kind of do this on my calculator of 5.2 degrees Fahrenheit, meaning that the temperature went up by 5.2 degrees Fahrenheit from 6 a.m. to 10 a.m. So I can now say my Fahrenheit temperature at 10 o'clock a.m. is going to be whatever it was at 6 o'clock, and that is that 64.5 degrees Fahrenheit, plus the change in temperature that must have occurred, 5.2 degrees Fahrenheit, and that's going to end up being 67.7 degrees. That's not right. It should be 60, wait. Yeah, that's right. It should be 69.7 degrees Fahrenheit. Sorry about that. Just did my adding a little bit wrong there. That was strange. Okay, sorry about that. 64 plus 5 is 69. I just about said 67. Very, very odd. My apologies for that. All right, and again, this particular prediction is within the data set, right? It's within the 6 o'clock to 11 o'clock that I had my sort of temperatures at. So we feel fairly good about this prediction. Now let's take a look at letter C. Use the rate to determine what the temperature would be at 3 o'clock p.m. This is known as extrapolation because this prediction is outside, or sort of extra, if you will, of the two known data points. Now again, what you can do in this situation is that you can either go from 6 o'clock a.m. to 3 p.m. or use our other data point at 11 o'clock and go from 11 o'clock a.m. to 3 p.m. Pause the video now and see if you can make a prediction of what the temperature should be at 3 o'clock p.m. All right, well, the AM PM thing here is a little bit challenging to deal with. I'm going to go again from 6 o'clock AM. All right, so from 6 o'clock AM to 3 o'clock PM, my delta T, think about this a little bit, from 6 to noon is 6 hours, plus 3 more is going to be 9 hours. Right? So I have a 9-hour change in time. That means my change in temperature, or my change in Fahrenheit during that time, is going to be 1.3 degrees Fahrenheit per hour times 9 hours. And again, you just want to like take your calculator out and go ahead and chuck that in. We don't need to do that here, but that's going to be, whoops, is going to be, got like a little bit ugly there. Didn't mean to move that one, but that's going to end up being 11.7 degrees Fahrenheit. And now my Fahrenheit temperature then at 3 o'clock p.m., it might be easier to use military time in this case, is going to be that 64.5 degrees Fahrenheit that we were at 6 a.m. in the morning, plus the change in my temperature, 11.7 degrees Fahrenheit, and we're going to end up at 76.2 degrees Fahrenheit. Sorry, that got a little bit ugly there. Now, you would get exactly the same answer if you started at the 11 p.m. mark, right? Remember, we have at 11 o'clock, it was 71 degrees Fahrenheit. That might even be a little bit preferable given the fact that you've got only 4 hours that pass between 11 and 3, and you've got kind of a nicer temperature to start there, but it wouldn't make any difference, right? It shouldn't make any difference because this is linear change. All right. Again, one of the things that we point out in this particular exercise is that, we've got these two data points, predicting between them, interpolation, predicting outside of them, extrapolation. Those two terms come up a lot in science, and so it doesn't hurt that bad to kind of review them here. All right, let's do a little bit more on linear change. So interpolating and extrapolating. Linear interpolation and extrapolation are very common in science. When we have two input-output pairs and no additional information, we will often use one of these two methods to predict unknown values. So let's take a look in exercise 3 at what's going on here. Physics students take two freeze-frame photos of a falling ball. From the photos, they find that the distance the ball fell after 1 second was 16 feet, and after 4 seconds it had fallen 256 feet. Letter A, real easy. Summarize the information given as two input-output pairs where time is the independent variable and distance is the dependent variable. All right, this should be a piece of cake. Why don't you pause the video really quickly and get those two input-output pairs down. All right, well, here we go. So what we know is that after 1 second, we've got 16 feet that it fell, and after 4 seconds, 256 feet. And it's kind of nice to have those just because you know what's coming in B. We're going to calculate an average rate of change, and it's kind of nice to be able to do that with two coordinate pairs because we're just calculating the slope of a line. All right, there we go. That was a nice ring on my Apple Watch. Let's take a look at letter B. Calculate the average rate of change from A. Using proper units, explain what this quantity represents. All right, so what I'd like you to do is pause the video now, calculate the average rate of change between them, right? Think about the units that are going on, and then tell me what that rate of change represents. Pause the video now while I try to make my watch not make any sound and see what you find. All right, simple enough, right? What we're looking at here is maybe change of distance, let's call it, divided by the change in time. That's going to be 256 minus 16, all divided by 4 minus 1, right? Again, we can just do all this sort of like on our calculator. We're going to end up 240 divided by 3. Maybe we don't even need our calculator, and that's going to be 80. Keep in mind, right, the numerator has units of feet. The denominator has units of seconds, so that's going to be 80 feet per second. Now, what does this quantity represent? It represents the average speed, is it a ball? Yeah, the ball is falling. The average speed that the ball is falling. Awesome. Great. Let's take a look at letter C. Use B and linear interpolation to estimate the distance the ball has fallen after 3 seconds. So we know how far the ball has fallen after 1 second. We know how far it's fallen after 4 seconds. So since we want to know the distance it's fallen after 3 seconds, and 3 falls between 1 and 4, we're doing linear interpolation. Pause the video now and see if you can figure that out. All right, well again, I'm going to start at this point so I can kind of go forward in time. From t equals 1 to t equals 3, obviously our delta t is 2 seconds, right? 2 seconds have passed between 1 second and 3 seconds. So the amount that the ball has fallen, just the amount that the distance change between 1 and 3 seconds is going to be 80 feet per second, right, times the 2 seconds that have elapsed, and that's going to be 160 feet. So I can now say the distance that it's fallen after 3 seconds, or at least using linear interpolation, I'm going to say is 16 feet, plus that change in feet, which is 160, and that's 176 feet. Okay? That's it. Linear interpolation, 176 feet. But, and I'm sure there's probably some physics students and physics teachers that might be watching this right now going, hey, wait a second. The distance that it fell after 3 seconds wouldn't necessarily be 176 feet. So let's take a look at letter D. Why might the estimate from C not be accurate? So why is it that perhaps that 176 feet would not be accurate? Pause the video now and see if you can give me an answer. All right, well, hopefully you understand that if I drop an object and it starts to fall, generally speaking, within the first few seconds, the speed is actually going to always be increasing. And so it's not likely that the speed from 1 to 3 seconds is exactly 80 feet per second. That's certainly the average speed between 1 second and 4 seconds. Definitely is the average speed. But the speed is actually changing throughout that interval because the object's speed is increasing, right? The object's speed is not constant. From t equals 1 to t equals, well, it's not constant at all, but I'll say from t equals 1 to t equals 4. So it is likely not 80 feet per second, right? Plain fact is the ball is speeding up. It's actually probably going faster from 3 equals 4 seconds, right? And actually the average speed from 1 to 3 seconds is likely going to be less than 80 feet per second. So that is probably an overestimate of what the actual distance fallen is after 3 seconds. Let's keep going. Oftentimes what happens though in science is if you don't know, right, if you don't have any idea, all you have are these two input-output pairs, you assume a linear trend between them and continuing forever afterwards to be able to make a prediction if you don't have any other information. Let's take a look at another example of this. Exercise number 4. In 1980, the population of the United States was 227 million. In 2020, its population was 330 million. If linear extrapolation was used, would the predicted population of the US in 2050 be more or less than 400 million? All right, so we don't know whether or not the population of the United States is linear. And we certainly don't know going forward in the future whether it's linear. Maybe it's going to kind of maybe it's going to level off, or maybe it's going to kind of increase exponentially. We don't know, right? But since we don't know, we might as well use a linear trend to say, well, I know what it was in 1980, I know what it was in 2020, and I'll just sort of draw a line between those two data points and keep going until I hit 2050 to see whether or not the predicted value will be greater than or less than 400 million. Pause the video now and see if you can make your way through this. Start by figuring out what the rate of change is of the population, and then go from there. Take some time to do that. All right, well, let's first get down some of our information just in sort of like coordinate pairs. So 1980, I'm going to say 227. I'm not going to include all the zeros for the millions and stuff. We'll just know that we're in millions. And in 2020, right, our population was 330 million. Right, so the first thing I might want to do is just figure out what the rate of change is. The change in population over the change in time. So I can do that by saying 330 million minus 227 million, all divided by 2020 minus 1980. Okay, and I can like do that all at once if I want to. What I'll find out is that, you know, on the numerator, I've got 103 million divided by 40 years, and that actually ends up kind of being a decimal, but that's okay. 2.575, and maybe I'll just tag a little million per year. Now, before we move on, let's just talk about this a little bit, right? What we're seeing here is that we have an average rate of change of 2.57 million people per year. In other words, the population grew, right, in the United States from 1980 to 2020 by 2.575 million people per year on average. I'm sure there were some years where it grew faster than others and some years where it grew slower than others. But on average, that's how much it grew. Now I want to try to use that to figure out or to predict the population in 2050, a year that hopefully hasn't come yet while you're watching this video. If not, this is a very dated video. So let's now go into that. We now want to know what our population is in 2050. And we can either use our population in 2020 or our population in 1980. But I think I'm going to use my population in 2020, okay? Plus the change in population that's going to occur between those two. Now the change in time is going to be 30 years between 2020 and 2050. So we can use that to figure out that my change in population is going to be 2.575, right, times my change in time, 30 years. So the population growth between 2020 and 2050 is predicted to be 77.25 million, right? Our population is predicted to grow, if we continue to grow at that rate, by 77.25 million people, which means my population in 2050, I can now predict to be, what was my population there? Oh, 330 million plus 77.25 million, and that's going to be 407.25 million people. So we are going to say greater than 400 million, right? Maybe there's just some kind of like, you know, we're just trying to figure out something like, well, maybe 400 million is some kind of magical mark, right? That we're curious to see if we will have hit by that point in time. Now again, you never know what's going to happen. Maybe we'll have a huge influx of immigration between now and 2050. Or goodness knows, maybe we hit another global pandemic. Hopefully not, and maybe population growth slows down, right? Lots of things can affect what's going to happen in the future, and that's why extrapolating, right, predicting outside of our data gets a little bit more dicey, a little bit more dangerous than interpolation, right? If we were using this to predict what the population was in the year 2000, well, that would be kind of cool because we could predict it and then actually compare it to what the population was in 2000. But oftentimes we want to predict things that haven't happened, not things that already have. So let's take a look at one last problem. Exercise number 5. A weather drone is used to measure the air temperature at 2 different altitudes above the ground. It measured the temperature at 400 meters above the ground to be 26 degrees Celsius, and at 2,700 meters above the ground, it measured the temperature to be 11 degrees Celsius. Letter A, what would linear interpretation predict the temperature to be 1 kilometer above the ground? Now, I'd like to have you do this on your own again, all right, but a couple things to note. One, the temperature is decreasing here, right? At 400 meters above the ground, the temperature is 26 degrees Celsius, and at 2,700 meters above the ground, the temperature is 11 degrees Celsius. That means your rate of change is going to be negative. It's also going to be very, very small, all right? So what you want to do is definitely carry quite a few decimals, all right? Or leave it exact as sort of like a fraction, if you will. Either way, okay, see if you can predict what the temperature is 1 kilometer above the ground. Pause the video now and see what you can do. All right, well again, I want to kind of lay all of this out in terms of like coordinate points and things like that. So we know that at 400 meters, we are at 26, and at 2,700 meters, we are at only 11. All right, so the change in maybe Celsius temperature above maybe the change in height, yeah, let's do it like that, right? We can say is 11 degrees minus 26 degrees, all divided by 2,700 minus 400. And that in fact does come out to be both negative and actually quite small and messy. I took it out quite a few decimal places, 0.00652 degrees Celsius per meter. And again, before we move on, let's just talk about this a little bit. The decimal does extend a little bit farther. It may have been wise to just use it in its fraction form rather than its kind of rounded decimal form. But I like to have this here just to really kind of illustrate that, yes, change is occurring. I mean, obviously, we went from like 26 degrees down to 11 degrees. But per meter, there's a very, very small change in the Celsius temperature per meter, right? Exceptionally small. So now let's use linear interpolation to predict what the temperature would be 1 kilometer above the ground. Now keep in mind, a kilometer is 1,000 meters. So what we're really trying to do at this point is figure out this. What is the temperature when the height is 1,000 meters? So let's go ahead and get into that right now. So I'm looking for, let's say, the change in Celsius, right? And let's say we do it from, actually, let me first do the change in height from 400 to 1,000, all right? And that's going to be 600 meters, all right? That means my change in Celsius is going to be negative 0.000652 times, not 600, times, not 400, 600. And that is going to end up being a change in my temperature of, actually I never figured out my change in temperature there, I just did it all at once. So let's kind of do this. Let's actually do my Celsius temperature at 1,000 is going to be that 26 degrees plus, or minus, depending on how you want to think about it, 0.000652 degrees Celsius per meter times 600 meters. I do that calculation all at once, and that ends up being a Celsius temperature of 22.1 degrees Celsius. All right. So I've got my starting temperature, 26 degrees Celsius, plus how fast my temperature is changing, and it's decreasing here, times how much my elevation changed. And again, I'm going from 400 to 1,000 rather than thinking about it as 1,000 going from 2,700 down to 1,000, right? Then it would be kind of a little bit messed up. I always like to sort of go have an increase in my independent variable, right? So my Celsius temperature at 1,000 is going to be my Celsius temperature at 400 plus the rate at which everything is changing times how much my elevation has changed, giving me a temperature of 22.1 degrees Celsius. Now let's look at letter B. If the drone carried a vial of water with it to an altitude of 500 meters, would linear extrapolation predict the water will be solid or liquid? All right, so here we're going to bring in a little bit of science as well. So what I'd like you to do, we already have the rate at which the temperature is changing. We really want to figure out whether that vial of water is going to be solid or liquid at an elevation of 500 meters. Pause the video now and see if you can figure that out. All right, well, let's do it. Now, I want my Celsius temperature at 5,000. Okay, I can figure that out by either using the temperature at 400 or the temperature at 2700. I think I'm going to continue to use my 400, so I'll do Celsius temperature at 400 plus the change in the Celsius temperature between the two. My Celsius temperature at 5,000 then will be, what was it? It was 26 degrees Celsius at 400 plus that negative 0.00062. All right, and the change then in my elevation is going to be 4,600 meters between the two. Okay, so when I crank through all of those numbers, the Celsius temperature at 5,000 then ends up being negative, whoops, sorry about that, negative 3.992 degrees Celsius. All right, and here's where we need to know a little bit of science, right? The freezing point of water in the Celsius system is 0 degrees Celsius. So, because this is less than 0 degrees Celsius, the water will be solid. Now again, it could be that the temperature doesn't change in this uniform way. Perhaps at some point the temperature changes more slowly than negative 0.000652 degrees Celsius per meter, right? Or maybe it even speeds up, right? Temperature definitely decreases as you elevate, which is why it's much colder at the tops of mountains than at their bases, right? Why we have snow at the top of a mountain rather than at the base of the mountain, all right? Simple as that. The question is whether or not it is a constant rate of change. All right, let's summarize. There are a lot of messy problems in that particular lesson, but the big point here is what is known as linear change. Linear change occurs when two variables change at a constant rate compared to one another. Now, when we know that, or we suspect it, or even when we assume it, we can then use that constant rate of change to do prediction. When the prediction comes between two data points that we have, we call it linear interpolation. When it occurs outside of the two data points that we have, it's called linear extrapolation. And as we pointed out a couple times in this lesson, linear extrapolation could end up being a little bit dicey in terms of how accurate the predictions are, because our assumption of linear change could actually be incorrect. All right. For now, I just want to thank you for joining me for another Algebra 2 lesson by eMath Instruction. My name is Kirk Weiler, and until I see you again, keep thinking and keep solving problems.